Welcome to our channel, Be Always Learner. By continuing the classification of systems, we are having another kind of classification is linear and nonlinear systems. The linear systems can be classified using the principle of superposition. The superposition principle states that the response to the weighted sum of input signals be equal to the weighted sum of outputs corresponding to each of the individual input signal. A system that satisfies the superposition principle is said to be a linear system. So for that, we are having certain representation that a linear system is having x1 as an input, then the system is having y1 t as an output. We can also represent it y1 t is equal to transformation of x1 t. In another way, if x2 is an input, then the system is having output y2t. The another mathematical representation is y2t is equal to transformation of x to t. The linearity is going to say that a system is linear if the input a x1 t, that is weighted input, this represents the superposition, b x2 t, where a and b are the constant terms, and that produces an output a y1 t plus b y2 t. So that should be the relation between the two kind of representation. Then we can write in the mathematical form, that is the transformation of a x1 t plus b x2 t transformation of this is equal to the constant term, then the transformation of x1 plus b transformation of x2 t. So that is the relation for linearity, that we are defining that the input, if this is the input, then we should have this much the output, right? So we are just putting the values of these two terms here. Now this is for the continuous domain, continuous time systems. For discrete time systems, that is the transformation of weighted sum of input is equal to the constant and the corresponding transform of the input so that is for discrete time systems. Now for that we can also represent that into the block diagram representation also, to make it more clear, that this representation on left hand side we can represent it like that we are having two inputs x1 n and x2 n. These kind of two input we are having. Then we are having two constant terms, that is a corresponding to x1 and b corresponding to x1. This is the multiplier. So this and this we encountered, then this positive sign here we are going to make a summer that is going to add these two quantity, and that is going to produce certain output, and after that we have to transform it. So for the transformation we have to make a system, and which is representing the transformation, and it is going to produce certain output yn. In the same way, you can design the block diagram for this representation, that we are having two input x1n and x2n, and individual same kind of system is there which is going to transform the input, and that is going to produce the output. And after that we are having two constant terms. One is this a corresponding to x1, we can write a here, and b corresponding to this x2, so this is b. And after that we are going to add it. So if a system is having certain this kind of representation, and I am going to represent it yn dash, if this yn is equal to y dash n, then the system is linear. Otherwise the system is non-linear. So if it's sustained, then system is linear system, and if yn is not equal to y dash n, then the system is non-linear. We can consider certain examples for the same. That let us start from one example, that dy t, the derivative of y with respect to time, is plus 3 into t yt is equal to t square xt. So if this kind of representation is there, then we can say that the system is a linear system. This is example for the linear system. We prove certain examples later on. In the next session we are going to cover certain example. One more example in the discrete domain, you can take that yn is equal to a into x of n plus b. This is the example for nonlinear systems. This b is going to make it nonlinear. That is extra offset we are providing to get the output, certain output from the system. I'll prepare one more video for the numerical of the same topic. Another classification is time invariant and time variant systems. A system is said to be time invariant if its input output characteristics do not changes with time. So for that we are having again one block diagram representation, that a system is there and that is having certain output, and that is also having certain input, right? So in the same way we are going to have certain xt as an input and certain yt as a output, and that is a time invariant system representation. So if it is so, then we can just graphically try to make it up so that it is convenient for you to understand. This is a certain input graph, and we are having certain output also. Rather, we are having four graphs to make it more clear, that we are having certain input that is represented by xt, and which is a function of time, and here certain output yt, which is a function of time also. So if I'm going to produce certain output, certain input like this, we are having certain input, and we are having certain output to the respective input, some amplification, right? If that is I am having, in the same way, if there is a delay in the input, there is a delay in the input, and there is a certain output with some same delay. So say this is t and this is t also, that is going to have a representation. So suppose same input I am going to produce, same input I am going to produce with some delay. The system is going to produce certain output, and we are going to see here that a system, if it is producing certain output, then the output, if the output is going to be the same one, then we can say the system is time invariant. So this is by definition we are knowing now. Now in the mathematical representation, that a system is having input xt, so after transformation the system is having output yt. If I am going to produce certain delay, and that delay is the amount of t, then after transformation the system is having output yt minus capital T, with the same amount of delay we are having at the output side. Then the system is time invariant, and if it is having the different response, then the system is having time variant characteristics. For a linear time invariant system, the coefficients of the differential equation for the continuous time domain describing the system are constant. If the coefficients are the function of time, then the system is linear time variant, right? So this is by definition for continuous time domain system. So for example, so we are having 2 d square y, double derivative of y with respect to time, plus 4 dy t by dt, the single derivative of y with respect to time, 5yt, is equal to 5xt. So you can see the coefficients are constant terms, then the system is time invariant. Otherwise, if I am going to represent the equation by say we are having a simple example, that is double derivative of y y plus 4 into t, the single derivative of y with respect to time, plus 5yt is equal to xt. Here the coefficient is having the term t. Coefficient is having the term t, which is depending upon the value of time. If it is so, the system is time variant. So this is time variant example, right? And this is time invariant example, time invariant example. So in this way we can understand the property of system. Another concept in this lie when we are going to the test the system for checking the property related to time invariant and time variant systems. So to test it, we are having a signal xt which is applied to the system, and we are going to find out the yt. Now after applying certain delay to the input side, and we have to find out the yt, that is represented by, this is for testing for time invariant property of a system. So for that, what we are saying, that we are having certain input xt with some delay capital T, and that is going to produce the output by transforming, and that output is represented by yt comma t. That is when we are producing the delay at the input side. And we are going to find out the y. The output. And now the next step is we have to delay the output by t, denoted by y t minus t, and we have to check the system for the output equation, and if this yt comma capital T, it means when we are producing the delay at the input side, must be equal to yt minus capital T for any value of t, then the system is called to be as time invariant. If it is not equal, the yt comma capital T is not equal to y t minus capital T, then the system is time variant system. For the discrete time systems, we are going to follow the same steps. That here we are assuming that we are having xn at the input side, and the system is going to produce yn at the output side. Mathematically we can define that yn is equal to the transformation of xn. This is for discrete time systems, DTS, right? So if I am going to produce the delay at the input side, how can I represent it? X n minus k. The kth amount of delay I am going to produce, and the transformation, and that is going to produce output y n k. In the same way, if I am going to delay the output by same amount, This is the first step. Second step is delaying the output. Delay the output. And we are checking the system that is represented by y and k. If again the same condition we can apply, that yn comma k is equal to yn minus k. If this is true, then the system is time invariant. Otherwise, the system is time variant. So this is also having the definition and for continuous time system and the discrete time systems. We are having certain examples for time, that if I am going to represent a system by yt is txt, these kind of systems are represented by property time invariant. We will prove it in the next session. And another kind of representation also we can have, for example, that yt is equal to xt square. These kind of examples for time variant. So we will have many numericals on the basis of these representation. We will explain all the numericals in the coming session. Another kind of system classification is stable and unstable systems that can easily be represented by some graphical representation. We are having in this that we are having certain input and having certain output. So with this relation we can represent it, that x1t is certain input and we are having corresponding output. Say suppose y and t, we are having output. On the time axis, x-axis we are representing the time, and say we are having certain limited we can say the input, right? This much of limit we are having for the input side. So we can just represent it by some dotted line. Say I'm going to say that my input is going to reduce like this. So that is kind of graph I am having for the input side, which is having certain boundation also. So we can say this is a bounded signal. So it is within the limit, and it is having certain output, and that output is represented, say, in this fashion. Say it is of this kind of representation. So this is again a bounded signal. This is again a bounded signal. Bounded signal within the limit, right? In the same way, we can say if the system is having certain input which is bounded by certain limits, and that is having the corresponding output which is bounded, then we can define a input signal xt is said to be bounded if it satisfy the condition that xt is less than n equal to certain limit, say mx is the limit, if the input is bounded by this limit for all the values of time, similarly the output is bounded if it satisfies the condition that is yt is bounded by certain my limit which is less than infinity for all the value of time. So this is the example for and definition for the bounded input, bounded output. So we can define now a system. A system is said to be stable if the bounded input, bounded output is there, and if every bounded input produces a bounded output. Say we are having a system and we are going to produce certain output corresponding to certain input. If this xt is bounded by a certain limit, as it is going to produce certain output, then the system is stable system. Otherwise the system is unstable system. It means if the bounded input is not having bounded output, then it is called to be as unstable system. Hope you like the concept and like the video. So please share it. In the coming session we are having lots of numericals we are going to perform. So please like and share and subscribe the channel.